Rooms. Welcome to Year. Today we will discuss about Heatsink design fundamentals. Friends, when designing or choosing the heat sink, the thermal engineer try to optimize the performance and the cost requirement. So basically, we will discuss about heatsink, which is used to mount the electronic components, and these electronic components generates the temperature, and this temperature we need to dissipate through the heatsink, and therefore the final heatsink design must meet the size, weight, durability, and cost target. Obviously, cost target is the main criteria for any company to generate the profit also. So this video is organized to help engineers and they're thinking around the numerous variables and the designing of a air-cooled non-pump liquid heat sink. So the topic which we will be covering are basic of heat transfer and thermal resistance and initial calculations. Then we will cover heatsink material selection, that is aluminum or copper heat pipes or vapor chambers. Then heatsink pin geometry, pin size, pin spacing and height. Then the final calculation of heatsink manufacturing and cost considerations. Friends, basically the thermal resistant drive delta T is the main thing that we need to consider in heatsink design. So, heatsink thermal performance is determined by adding each of the thermal resistance in the network and multiplying that number by maximum power output of the heat source. So here you can see this chip is the heat generating source. So here we have a vapor chamber. Then we use a solid epoxy that to fix with this with the base, and then we have base with the pins. So here you can see the heat mechanism, the heat transfer mechanism, here the thermal resistance. So here the heat generated by chip is transferred to the base via conduction, and from this base to pins via conduction. Then this heat from these fins to air is transferred via convection and radiation. And on this side, you can see the thermal resistance. Here we use material to fix this chip paste in between, that is the heat resistance. Then again, base will be the heat resistance. Then we use solder or epoxy to fix this, and that is also the heat resistance. And finally, the base and fins. Then fins to air, that is heat transfer coefficient. There will be some deviation because of heat transfer coefficient, and the air temperature rise from normal temperature, ambient temperature to the specific temperature. So this is the mechanism how it is going to work. Here we have considered material aluminum and the type metal, and here you can see the thermal conductivity watt per meter Kelvin. So here we have range of thermal conductivity and material. So here, as we have discussed in the earlier image, the material of fins or base will be aluminum, that will be a metal, and this will be the thermal conductivity. Similarly, for copper heat pipes and thermal grease or paste that we use to fix in between. So that will be the thermal interface, and here will be the thermal conductivity. Similarly, for thermal paste, graphite, phase change material, and thermal adhesives. So we have considered these materials in the earlier picture image, and these are the type and thermal conductivity range for that particular material. Now we are considering some assumptions in the heat design assumptions. So to simplify the assumptions, you can conduct the heat sink analysis by hand or using a spreadsheet. The output of these calculations will be the dimension of heat sink required to maintain the required heat source. However, these calculations are preliminary calculations, and for detailed calculations, now we are using software, specific software and tools and CFD analysis in order to verify the design. So in order to get a preliminary design, we can use such type of calculation, then final design can be carried out with the specific software or a tool. So what figure we have shown is the typical heat sink with the pin, and then we are mounting electrical components such as LEDs or chips on or microprocessors. So there are some fixed dimensions that we would need to determine to design the an appropriate heat sink. So in order to reduce the complexity of calculations, we have made some assumptions. The assumptions will be the surface area due to thickness of the fins. So T, small t, that we are considering the thickness of the fins, and the thickness of the base B are much smaller than the total surface area of the heat sinks. The thermal conductivity is the second point will be the thermal conductivity of heat sink is high enough so that temperature of surface of the heat sink is uniform and approximately equal to the temperature of the heat source. So we are considering equal temperature and heat distribution. So we are not considering any hotspot. Then the third assumption will be the heat source has same length and width of the heat sink and is centered on the base of the heat sink. So we are putting this heat source in the center of the heat sinks. Then fourth assumptions will be the heat source is in perfect contact with the base of the heat sink. So here we are considering that the surfaces of the heat source and the base will be perfectly aligned and there will not be any deviation or a gap in between. So it will match completely in 100% contact with the heat sinks. So the above assumptions, so what four assumptions that we have considered will introduce some error in calculation. However, the purpose of this calculation is to get rough estimate, and as we discussed, this is rough estimate that can be verified with the software or testing can be used to refine the design. So finally, we can make one prototype also, and then this fixing will be tested and verified with the calculations. So that will be the actual verification. So that will confirm the design. So one another assumptions that we made is the heatsink base is oriented vertically using or utilizing natural convection and radiation. So as shown in figure, so here we have this figure of heatsink. So these pins are vertically oriented and it will be generating, transferring the heat through a convection and a radiation. So here we will first see the natural convection calculations. The values for L and H are first chosen based on your heatsink design constraint. So this length and height of the heatsink can be selected based on your design constraints. So where it is going to be mounted and what will be the size of heat source and available space. The width W of the heat sinks, the width or the spacing between the fins S and the number of fins M will be calculated for the selected value of L and H. So the convection heat dissipation QC1 from area A1, the external side surface of the heatsink is shown. So here you can see the QC1. So this is the field and this is the side areas from which the natural convection will happen. So here there will be a heat transfer QC1 from the side surface of the heat sink. So here QC1 is calculated with this formula where Ts is the temperature of the heat source and T ambient is the ambient temperature. And to calculate the area I1, we have used this formula as shown here. So this is the basic formula to calculate the QC1. And in next formula, we will see how to calculate H1 also. Yeah. So the convection coefficient H1 that we have seen in the earlier formula for the area A1 is calculated using this equation. So this formula is for natural convection for vertical surface. The area A1 includes small areas of horizontal surface. The difference in the magnitude of the natural convection coefficient for horizontal and vertical surface is not so significant, and the horizontal areas are smaller relative to vertical surfaces. So, as such, utilization of equation for this equation for the entire area will not introduce significant error and will simplify the calculation. Now, the next step in this calculation is to determine the heat dissipation Q2 due to natural convection from the surface area A2. So, here we have this surface area A2 on the top. So, through this, there will be a convection heat transfer, and for this, we need to calculate the heat transfer. So, for this, we have this formula to calculate the area A2. So this we have seen earlier, and S optimum is the spacing between the two fields, and T is small t is the thickness, and B is the base area that we have seen in the earlier slide. So this is the formula for calculating the area A2. Now, so the optimum spacing between the fins as optimum that produces the maximum heat transfer due to natural convection. So if we space the fins closer to each other, then it will reduce the transfer. If we space fins away from each other more than the required, then also it will not optimize the heat sink. So in order to optimize it, we need a proper spacing between the fins. And in order to calculate that proper spacing between the fins, we have this formula. So internal surface areas of the fins and the convection heat transfer coefficient can be maximized. So here we have this is the acceleration due to gravity small g, then beta 1 by T average is the expansion coefficient with the thermal temperature unit in Kelvin. So here as we discuss Ts and Tf in the earlier slide, so we have this formula for optimum spacing. We will see what this means in the next slide. So here T average will be Ts plus T ambient by 2, where alpha is the thermal conductivity of air elevated at T average. So temperature average at average temperature, this will be the thermal diffusivity, and this is the kinetic viscosity of air elevated at T average. So we get the average temperature and the convection heat transfer coefficient between the fields, as we discussed in the earlier slide, is given by the equation H2 1.31 K by S optimum, where K is the thermal conductivity of air at average temperature. So this is the formula for heat transfer H2. Now the area used to calculate the heat dissipation from the heat sink, the air heat dissipation QC2 from area A2 here due to natural convection is calculated using this formula QC2 H2 A2 Ts minus T ambient. So the convection coefficient H2 for vertical surface located between the fins. So this convection coefficient is used for small horizontal areas as well, so this will occur less error because the area is very small. And this is how we have calculated the heat transfer through side surface and the top surface QC1 and QC2 for the convection. Now we have another heat transfer that is due to radiation. and we need to calculate radiating heat transfer energy. The contribution of radiation heat dissipation is quite significant for naturally cooled heat sinks. So here is the formula to calculate the heat radiation QR1, and here you can see as we discussed earlier in this image. So here you can see this will be the radiation from side and from the top and bottom. So similarly to QC1 and QC2, we will have QR1 and QR2. So that will be due to radiation, it transfer due to radiation. And here you can see the variable is surface emissivity of the heat sink. The typical values we get through the importance article. There is another article, the importance of heat radiation in the heat sink design. The Stephen Boltzmann constant has the value of 5.67. This is watt per meter square Kelvin. So this is the value for this constants. This value we can get from this another article, and then we have area and temperature. So we get QR1. The next radiation heat transfer from area A2 given by the equation is calculated with this equation. Similarly, QR2 with the area 2. So the radiation calculation we have done with the QR2, and for that we need area AR2. Here is the calculation how we have done for area R2. So here you can see AR2 for QR2, and these are the sizes of pins, spacing and length and thickness and height. So this can be easily obtained with this calculation. So the final heat calculation will be the final step is to calculate the number of pins, and we can calculate number of pins with this formula where uh, the N needs to be dissipate heats at a temperature Ts. With the number of pins known width, we can easily calculate with this formula. The law of conservation of energy dictates that the heat generated by the heat source must be equal to heat dissipated by the heat sink. So whatever heat will be generated by a heat source, whether it will be a chip or any other electronic equipment, that must be transferred or dissipated by the heat sink under the steady state condition, and that is the basic assumptions and consideration for calculation of number of pins. Here you can see this equation we can use to calculate number of pins. So this notation is nothing to calculate rounding up the nearest integer, because number of pins will be exact number and not the fraction one. So we consider this, let's say 3.4. If it comes 3.4, then we need four number of pins like that. So then we have another formula to calculate the width of the heat sink. So with this formula, we can calculate the width of the heat sinks, because width of the heat sink depends on the number of pins. So if number of pins are more, then we need more width. If it is less, then we need a less width. So this is the formula with which we can calculate the number of pins. So these are the simple calculations. In fact, this are derived, these formulas are derived with some assumptions and optimization of heatsink. So if you want to minimize the volume of the heatsink, because ultimately the cost of heatsink will depend on the volume of the heatsink. And so it is possible to optimize it. So this will maximize the heat transfer also and reduce the surface area needed to limit the heat source. And we need to validate it with the further CFD analysis and thermal analysis software and actual tests we can perform with the prototype and validate the design. So friends, I hope you will like this video. Thank you very much and happy learning.